In this video, we're going to discuss buffer capacity, or the limits of a buffer solution. So let's take this ammonium buffer. I've got ammonium breaking into H plus and ammonia. It's got a Ka of 5.6 times 10 minus 10. pK is 9.25. Depending on how much ammonia and ammonium you have, you'll get different pHs. Remember that our pH is equal to the pKa plus the log of the base concentration divided by the acid concentration. As we adjust the amount of acid and base, this will shift our pH. But there's a practical limit to how far we can really get these concentrations from each other and still have a buffer solution. Let's imagine a situation where we have 1 molar ammonium and 0.1 molar ammonia. We can find that pH pretty quick. 9.25 plus the log 0.1 over 1. My pH will be 8.25. The log of effectively a tenth is minus 1. Makes sense. We have lots of acid around. We should be a little bit more acidic. The pKa would be the pH if we had equal amounts, and we're a little bit more acidic, so our pH is a little bit more acidic. Well, to this buffer, let's add 0.3 moles of NaOH. Well, I'm adding a strong base. Let's assume we're in 1 liter, so our molarity is equal to our moles. If I'm adding 0.3 moles of sodium hydroxide, that's going to give me some new concentrations. I'm going to go down to 0.7 molar ammonium, and I'm going to go up to 0.4 molar ammonia, which we could plug back in. Hey, what's my pH in this case? 9.25 plus the log of 0.4 divided by 0.7. 9.01. And you could do it again. You could add 0.3 mole of sodium hydroxide again. This is going to change our ammonium. It's going to go down to 0.4. And it's going to bring our base ammonia up to 0.7. We can solve that pH as well. 9.25 plus the log. In this case, the 0.7 is on top, 0.4 is on the bottom. pH is 9.49. And if we check, well, originally we had more acid than base, and so we were lower pH than our pKa. Second, we still had more acid than base, and 9 was lower than 9.25. But now we have more base than acid. 9.5 is more than 9.25. We're more basic, which is where we were headed as we kept adding sodium hydroxide. Take it a little further, let's add 0.3 mole NaOH again. Going to go down 0.1 ammonium and up to 1 ammonia. pH is 9.25 plus the log of 1 over 0.1. My pH is 10.25. So far, our buffer has successfully inhibited a great deal of pH change. Granted, we have changed in total by 2 pH units, but we've added almost an entire mole of hydroxide. 1 mole of hydroxide in a liter of water would be pH of 14. And so we've drastically prevented that shift. The problem is, what if we do it again? But then we run into a problem. Let's add 0.3 mole of NaOH one more time. But I don't have enough weak acid to consume all of that. I have 0.1 mole of weak acid left in my liter. It'll wipe out 0.1 mole of this hydroxide. There's just 0.2 mole NaOH left. I'll have effectively no weak acid. I'll have 1.1 weak base. So my weak base could perform an equilibrium and create a very small amount, but I've got all this hydroxide just dominating. I have a strong base hanging out. In fact, it's 0.2 moles per liter, so I have 0.2 molar hydroxide from it. My pH is now 13.3. So previously, each individual addition raised us a little bit. There was 0.75, there was 0.5, there was 0.75, and the next one, 3. Because the next one really isn't about a buffer. The next one's about just pure hydroxide floating around, leftover strong base. Our buffers can run out. Eventually, they can get so low in concentration that the next addition of strong acid or base will completely wipe out any more of the buffer capacity. So what ranges are our buffers good for then? Where are they likely to still be usable? In general, when our concentrations are, as we've shown here, when they're within a power of 10 of each other. So you can have 1 and 0.1, or you could have 0.1 and 1. These could be scaled up or down from each other. You could definitely use 0.02 and 0.2, as long as they're within a power of each other. This is where our buffers are most effective. As a result, we can see from our data here that at those two extremes, we are plus or minus 1 pH unit from the pKa. 9.25 is when we have our ammonium and ammonia equal to each other. When we had 10 times more acid, we were 1 pH unit smaller. And when we had 10 times more base, we had 1 pH unit larger. This tends to be the range of a buffer. So your capacity is when you'll run out of the chemicals from addition, but your range is where making additions of strong acid or base are still reasonable to inhibit those pHs. Our range tends to be plus or minus 1 from the pKa. Attempting to use a weak acid and base mixture to set a pH outside of this range is rather difficult, as very tiny changes to the concentrations can begin to change that pH dramatically.